Hello, welcome to a little video on how to make a phi map. If you know a little bit about phi, you'll recognize this number right here, 1.618. That is a number like pi. It goes on forever. And there's a 0 right after the 8, so it makes a very clean break right there. So we end up with 1.618. And it is used as a multiple or a divider. So we'll have some number, a will be our primary number, and then we will multiply or divide it by 1.618, phi, and that will create our second number, b. So whatever, and then a plus b is going to equal c, and that's how you build the sequence. You can just perpetually build the sequence using that relationship, as long as you use squares. You have to use squares every time. I'm representing C here as a rectangle because what we ultimately create is two different shapes out of this. We use two squares to create a rectangle. So squares and rectangles are intimately connected to this process. And A plus B equals C is the same equation that Fibonacci uses, which is basically the reason why phi and Fibonacci are about the same thing. These are two geometric ways in which we can find phi. You take a circle, put a equilateral triangle in there, find the center of the triangle, and then mark that line and that line. Similar with a square is right on the center line of the circle and the vertical center line bisecting the square, and the square up until it touches those points, and you'll get that. So then phi is represented as essentially areas or lines. And that's it. That's it. It's all just multiplying and dividing by 1.618. That's all it is. That's how phi is so simple. And the beauty of phi is how it will take that very simple equation and build just this huge myriad of complexity out of it, which is what's so interesting. So that first equation is a plus b, and then we have the option of c. So when we're creating phi maps, we want to always maintain a phi rectangle. That's the whole point of the thing. So you can see here there's a phi rectangle of a and b, and it's filled in with this little square, with these squares, which are just continuing that cycle on down, just to show the full rectangle. So we have a plus b equals c. So then we have, this is our primary question. This is the first choice that we have. And you can either go below on these two, or you can go above on these three. And by making one choice or the other, you are maintaining the phi rectangle, but you're creating a fundamentally different pattern. So whichever one you choose, you have to maintain that and just carry your pattern through. And what comes out of it is these two different patterns. So this one is the classic phi spiral pattern, in which it's just ever spiraling either out or in. They both go in both directions. And that we get by always putting the new square on top of the 3. If we do like Fibonacci and we do a direct a plus b equals c, and always put the c on the side of 2, like this, then we get this pattern, which illustrates this line right here, which is a 45-degree angle, and all these squares keep reinforcing, pointing at it. And those are the two fundamentally different types of phi patterns. So we've got two different shapes, the square and the rectangle, and we've got two different sequences, two different patterns that come out of it, above or below, line or circle. So it's just fundamentally rooted in duality. So then, exploring geometries that exist within those patterns, the most simple way to do it is to just isolate individual building blocks. So our two primary building blocks are the square and the rectangle. The easiest way to show the geometry in a square is by using a circle. The easiest way to show geometry in the rectangle is using an oval, or they're the same relationship. So a quarter circle, if the square is a quarter of the circle, it's going to create this line. And that is that's the line that creates the phi spiral. So we're going to stick with that. We're going to add this also, this bisecting linear line. And then if we infer that line existing on the opposite side, then we're going to get this kind of seed shape. And that's this. And that is the primary geometry existing in phi. Or in a square. There are definitely more if we, put these arcs on the center point, or maybe even bisected them like here, how I've done here with the center point. But this is a very simple way to do it, and we're just going to stick with that. And since we are using this, then we'll do the same thing for the rectangle and create this shape using the oval. Once we have those two, then we create a phi sequence of descending or ascending scales. And what we're going to find out is that there are only two ways that these patterns can exist relative to each other. One is this way, where the bottoms are touching, and the other is this way, where the bottoms are not touching. And that's it. There's no other way to connect them. And the same thing happens over here. There's only two ways that these relate, either like that or like that. Now this square is, right off the bat, fundamentally different. You can see that the whole square is rotated sideways. And we have to do that because it maintains the phi relationship as a building block. First of all, that's what's happening here. You can see that it's always a square and a rectangle. Phi is always, and over here too, it's always a square and a rectangle. That's part of the effect of A plus B equals C. Is C is always going to be a square. So if we took this one and did it this way, it just wouldn't work because it doesn't create a square. So it has to stay like that, which reduces us back to our two choices. So interestingly, what happens is that the square wants to use this pattern where the bottoms touch, and the rectangle wants to use this pattern where the bottoms don't touch. So they've each got two options, and they're both using different options, representing different shapes. So again, deep duality there. Then we would take those and create sequences out of them, or plug them into, so whichever relationship we're going to choose, if the bottoms are going to touch or not, then we maintain that all the way through. And then just verbatim move this square into here, like that, and move this square into here like that, right? And then we get this pattern. So we use this sequence, and we end up with this pattern. Then if we mirror that sequence, same thing, haven't changed anything, just mirrored it, then we get the fundamentally different sequence, and we just verbatim put those in. We get 3 spirals. It's hard to tell here because there's not enough squares, but ultimately this is creating 3 spirals. This creates 1, that creates 3. And you can see the master shapes down here. Then we extract the shapes from these patterns, and this is what we end up with. And those are the master shapes that we're going to use to create maps. So we've got fundamentally a square map that also exists as circles, and then we've got these 2 different patterns. And that applies also to the other style of map, this one. See, really comes from the corner, that goes into the center. Not the center, but its own center. And represented as circles, and we get these 2 basic ways of reading the lines. We've got these 2 linear projection lines, and we've got this oscillating linear line, and then these 2. So they're always just elements of each other, right? And they come from one sequence mirrored, showing the opposite relationship between these 2 leaves. Connected, not connected. Crazy. And there's lots of different ones we could do there, but those are the most simple ones. So then once we have our different forms, then we compile those forms into create maps or harmonic wholes. So they will, the way they go together is we take simply one full form. So in this case, it's going to be a square map, a square phi map. Then you can see that it's offset. So this experience here happens in each area because you can't say where it happens. And we're using the map to explore all the different possibilities. So in every single way that this map can go into itself, we have to put it there. But we can't ever break through the phi rectangle boundary there. So it just always has to stay within the phi rectangle. That's our primary boundary, and everything exists within that. We want to know what exists within that. So at its own scale, it will create 4 variations of itself, and those all fit together, and that's a primary map. But you can see that it's not as detailed perhaps as we'd like. So we can go to a second level, which is we take that same map, reduce it down 1 scale so it reaches that width, and then insert those into there. And you can see that we can put one cleanly right there. It creates that rectangle already. Then we can put the other one in here, and there's not really room enough for a third one. A third one doesn't fit perfectly, so we'd have to invoke some judgment in there, and we don't want to do that. Let's just leave it connected to the perimeter, because that's all we really know for sure. Everything else is just hearsay, I guess, in some ways. And that's going to require 6 maps to do the job. So we've got ultimately 10 maps inherent in 1 here. And you can see also that they don't reach the bottom, so we have to do 2 of them. And when we do all of that, put all our maps together in 2 different levels and all the different potential spots, we get this. And that is a phi map, a square phi pattern map. So with all of these shapes, we can do that same thing. And that is really all there is to it. So quickly, you've got 2 different ways to do it. Above or below, it's going to create one of these 2 patterns. And we're going to interpret those patterns as through the geometry of a square and the geometry of a rectangle. And we're going to sequence those geometries in a particular way that forms one of these patterns. Then we're going to extrapolate the shapes from those patterns and use those shapes to create their own individual maps. So any pattern that you can reasonably find in a phi rectangle, you can extrapolate into a map. And then once we have the different types of maps, then we can take it 1 step further if we want to. Usually I just use the straight rectangle map because it's got good information. Itself is a piece of information. The square is a piece of information too, but the rectangle is a better piece, in my opinion. And but to create a square out of these maps, we would have to do a similar thing where we'd take 4 of them and fit them together until they fill in all of the gaps. Now you could argue we don't need this one, and maybe we don't. It could be redundant, but, well, it's not redundant because, see, it fills in some other information there. So then we get a square map created by our phi map. Then we can take these maps and overlay them onto photographs and see if we can find various relationships within the photograph. So here's some people in a built environment, and there's all kinds of fun stuff that we could read into that. And that will be the purpose of a number of the following videos. Hope that was helpful. Thank you very much. Hopefully you'll join me on some of the other videos, and we will see you there. Take care. Be safe. Bye.